This video is for those of you who are studying for your physics midterm exam or even your physics final exam. And if you're currently in high school or in college, you could still benefit from this video. So it only contains multiple choice problems, and I'm just going to run down through a list of topics that is going to be in this video. We're going to talk about one-dimensional kinematics, speed, velocity, acceleration, displacement, things like that. Also graphs of linear motion. We're going to talk about projectile motion, vectors, and then we're going to go into forces, Newton's law of motions, free body diagrams, inclined planes, pulleys, friction, tension force, normal force, stuff like that. And then we're going to move on into circular motion, gravitation, centripetal force, working energy problems, kinetic, potential energy, mechanical energy, conservation of energy, linear momentum, inelastic, elastic collisions, impulse momentum theorem, rotational motion, torque, inertia, angular momentum, and other topics in those chapters. So I just want you to know what topics will be in this video in case you may have to study for topics that this video might not cover. So let's go ahead and begin. By the way, I recommend that you pause the video and work out each problem yourself before viewing the solution. The best way to learn is by doing the problems. So just make sure you pause the video, and once you finish, unpause it to see if you have the right answer. So let's go ahead and begin. Number 1, a car travels 200 miles east in 4 hours and then 300 miles west in 5 hours. What is the average speed of the car for the entire trip? Average speed is equal to the total distance divided by the total time. So what's the total distance in this problem? The car traveled 200 miles east, and then it went 300 miles west. So it traveled a total distance of 500 miles. And the total time is 4 hours plus 5 hours, so that's 9 hours. So all we got to do is take 500 and divide it by 9. So the average speed is 55.6, or 0.5 repeating, miles per hour. So that's the answer. It correlates to answer choice D. Number 2, a car travels 200 miles east in 4 hours and then 300 miles west in 5 hours. That's supposed to be an S. What is the average velocity of the car for the entire trip? So, how is this problem different from the last problem? How can we calculate the average velocity of the car? The average velocity is equal to the displacement divided by the total time, as opposed to the total distance over total time. So what is the displacement of the vehicle? Well, we know it travels 200 miles east, and then it travels 300 miles west. You need to understand that distance is a scalar quantity. It can only be positive. Displacement is a vector. It can be positive or negative. So the displacement for the first part of the trip is positive 200 because it was going in a positive x direction. And then going west, it's negative 200. So if we add these two values, the net displacement for the entire trip is negative 100 miles. Because we started here, and the net result, if you look at the initial position to the final position, the car traveled 100 miles west. Now the total time is still 9 hours. So it's going to be negative 100 divided by 9. And so this is going to be negative 11.1 miles per hour. So keep this in mind. Speed is always positive, but velocity can be positive or negative. Velocity is a vector. It has magnitude and direction, but speed is a scalar quantity. It has magnitude only. So D is the right answer. Number 3, a car accelerates from 15 meters per second to 45 meters per second in 9 seconds. How far does the car travel during this time period? Now for these types of problems, you may want to make a list of what you know and what you need to find. So we're given the initial speed is 15 meters per second. We have the final speed, which is 45 meters per second, and the time period is 9 seconds. Our goal is to find the distance that the car travels, or its displacement. Distance and displacement is the same whenever the car travels in one direction, if it doesn't change direction. The equation that we need that has all of these variables is this one. It's 1/2 v initial plus v final multiplied by t. So you can only use this equation if the car is moving with constant acceleration. It can't be moving with constant speed. So it's going to be 1/2 the initial speed plus the final speed multiplied by the time. 15 plus 45 is 60, and 60 divided by 2 gives us an average speed of 30 meters per second. 30 is the average between 15 and 45. So it's going to be 30 times 9. 3 times 9 is 27, so 30 times 9 is 270. So it's 270 meters, which means C is the right answer. Number 4. Which of the following statements is not true concerning a ball in projectile motion that was kicked horizontally off a 200-meter cliff at an initial speed of 15 meters per second? So go ahead and try this problem. So let's begin with a picture. So here's the ball. It's kicked horizontally off a cliff, and it follows this trajectory. So the initial speed is 15 meters per second, and the height of the cliff is 200 meters. So which of the following statements is not true? So let's start with A. The initial vertical velocity, is that 0? At this point, the ball is moving in the x direction. It's not moving at an angle. It has no y component. So whenever an object is moving horizontally, the vertical speed is always 0. The only way the vertical speed will not be 0 is if it's moving at an angle, if it's moving straight up, anything but horizontal motion. So anytime it's horizontal, Vy is 0. So A is the true statement. Now what about E? The horizontal speed is constant. Is that true or false? And what about B? The horizontal acceleration is negative 9.8 meters per second squared. Now, whenever you have an object that's moving in projectile motion, by definition, the only force acting on the object is gravity. So there's no air resistance, nothing else. So therefore, gravity only acts in the y direction. So we have a vertical acceleration of negative 9.8 due to gravity. Since gravity is the only force acting on an object in projectile motion, by definition, there is no horizontal acceleration. It has to be 0, which means B is a false statement. The horizontal acceleration is not negative 9.8. That's the vertical acceleration. That's AY. AX is the horizontal acceleration. Now, E is a true statement because if the horizontal acceleration is 0, then the velocity, Vx, is constant, which means the horizontal speed is constant as well. Now, since Vx is constant, that means C has to be a true statement. So let's call this point A, point B, and point C. Because Vx is constant, everywhere along this trajectory, the horizontal speed will be 15 meters per second. That's not going to change. Anytime the acceleration is 0, the velocity will be constant. And so the horizontal speed is always 15 meters per second everywhere along this curve. Now what about D? D is also a true statement. Notice that the vertical acceleration is negative 9.8 meters per second squared. The acceleration tells you how much the velocity changes every second. So because AY is negative 9.8, that means the vertical velocity will change by 9.8 meters per second every second. The negative sign tells us that the velocity will decrease by 9.8 meters per second every second. Now, on the other hand, AX is 0, which means that the velocity in the x direction does not change, which explains why Vx is constant. So therefore, the only statement that is not true is statement B. The horizontal acceleration is not negative 9.8. It's 0 whenever you're dealing with projectile motion. So make sure you keep this in mind. For projectile motion, AX is always 0. AY is negative 9.8, always. Vx will always be constant. And Vy is 0. Let's say if you're going in this direction, at this point Vy is 0. Anytime you have an object moving in the x direction, Vy is 0. So if you get a projectile that looks like this, at the very top, the vertical speed is 0 because it's moving horizontally at that point. And keep in mind that Vy changes by 9.8 meters per second every second. So if you're dealing with velocity, the vertical velocity always decreases by 9.8 meters per second every second. Number 5. A ball is released from rest at the top of a 450-meter cliff. How long will it take the ball to hit the ground? So let's start with the picture. That's the cliff, and here's the ground. So it's 450 meters high. So here's the ball. Now it's released from rest, which means that the initial speed in the y direction is 0. How long will it take for it to hit the ground? What equation should we use? We can use this equation. The displacement is equal to v initial t plus 1/2 at squared. Now we're dealing with the vertical displacement, so we need to use the initial vertical speed and the acceleration in the y direction. The displacement in the y direction as we move from position A to position B is negative 450 because we're going in a negative y direction. Vy initial in this problem is 0, and the acceleration in the y direction is negative 9.8. So what we have is negative 450 is equal to negative 4.9 times t squared. So negative 450 divided by negative 4.9, that's positive 91.837, and that's equal to t squared. Now let's take the square root of both sides. So t is 9.583 seconds, which means E is the answer. Number 6. A ball is thrown downward with an initial speed of 25 meters per second from the top of a 500-meter building. How long will it take the ball to hit the ground? So in this problem we have the same picture, but this time the ball is thrown down with an initial vertical speed of 25 meters per second. And the height of the building is a little bit different. It's 500 meters this time. However, we could use the same formula to calculate the time. So the vertical displacement is going to be equal to the initial speed multiplied by the time plus 1/2 at squared. Now the displacement in the y direction as we move from position A to position B is still negative. It's negative 500 in this example. And the velocity in the y direction is negative as well because the ball is moving in a negative y direction. So this is going to be negative 25 times t. And A is negative 9.8. Half of that is negative 4.9. So a positive and a negative sign will be a negative sign. So this is the expression that we have. We have a quadratic expression or quadratic equation. So we need to use the quadratic formula to solve for t. So let's take everything from the right side and move it to the left side. So this is going to be 4.9 t squared plus 25t minus 500, and that's equal to 0. Now let's use this formula. T is equal to negative b plus or minus the square root of b squared minus 4ac, all divided by 2a. So in this problem, a is 4.9, b is 25, and c is negative 500. So this is going to be negative 25 plus or minus the square root of 25 squared minus 4 times a times c, divided by 2a, which is 2 times 4.9. Now I'm going to do this step by step so you won't make any mistakes. 25 squared is 625. Negative 4 times 4.9 times negative 500, that's positive 9,800. And 2 times 4.9 is 9.8. So now let's add 625 plus 9,800. So now what we now have is negative 25 plus or minus the square root of 10,425 over 9.8. The square root of 10,425, that's going to be 102.1. Now there's two possible answers. We can do negative 25 minus 102.1, and that's going to give us a negative number, or we could do negative 25 plus 102.1, and that's going to give us a positive value. Now since time can't be negative, we're going to choose the positive answer. Negative 25 plus 102.1 is 77.1. And then let's divide that by 9.8. And so this is equal to 7.867. So that's how long it takes for the ball to hit the ground if it's thrown downward with this initial speed. So D is the answer. Number 7. The velocity of a rock in component form is v is equal to negative 12I plus 5j. What is the speed of the rock and its direction with respect to the positive x-axis? So what you need to know in this problem is that the number that's in front of the letter I represents the value of the x component, and the number in front of the letter j represents the y component. Now, if you have vx and vy, you could find the magnitude of the velocity, which is equivalent to the speed, using this equation. So v is going to be the square root of negative 12 squared plus 5 squared. Negative 12 squared is 144, and 5 squared, or 5 times 5, is 25. 144 plus 25 is 169, and the square root of 169 is 13 meters per second. So that's the value of the speed, which means we could eliminate answer choice A and B. Now the next thing we need to do is calculate the direction, or the angle. So we can graph it using the components. So let's draw a graph. So the x component has a value of negative 12. So we have to travel 12 units to the left. The y component is positive 5, so we got to go up 5 units. And the hypotenuse of the right triangle that's formed is 13, which is the magnitude of the velocity. First, we need to calculate the reference angle, but our goal is to find the direction with respect to the positive x-axis. So this is the angle we need to find. So the angle is arctangent, that is the reference angle, Vy divided by Vx. Now, just make everything positive, and this will give you a positive reference angle between 0 and 90. So the y component is 5, and the x component is negative 12, but we're going to make it positive 12. So the reference angle, the angle inside the triangle, is 22.6 degrees. However, we need to find this angle. Now, this measure is 180. That's basically the angle of a straight line. So we need to find this angle, which is 180 less 22.6. So if we take 180 minus 22.6, that angle is going to be 157.4. Now we know the answer has to be between 90 and 180 because the triangle lies in quadrant 2. This is quadrant 1, quadrant 2, quadrant 3, and quadrant 4. So now we have the direction is 157.4 with respect to the positive x-axis. So therefore E is the right answer. Now for future problems, whenever you need to find the angle in quadrant 1, it's going to be equal to the reference angle, which you know how to find it using this formula. Just make sure everything is positive. If the triangle is in quadrant 2, like what we had in our example, it's going to be 180 minus the reference angle. If it's in quadrant 3, then the angle relative to the positive x-axis is going to be 180 plus the reference angle. And in quadrant 4, it's going to be 360 minus the reference angle. Number 8. A ball rolls horizontally off a cliff at 23 meters per second. The range of the ball is 184 meters. How high is the cliff? So here's the picture that we have. We're given the initial speed of the ball, 23 meters per second. And then it's going to follow this trajectory. And the range is 184 meters. So that's how far it travels in the x direction. How far does it travel in the y direction? So that distance is going to be the height of the cliff. Now the first thing we need to do is find the time of travel. How long does it take to go from point A to point B? So how can we figure that out? Well, we do have this equation. The range is equal to Vxt. The range is basically the horizontal displacement. We know d is equal to vt. Anytime an object is moving with constant speed. So we have the range is 184 meters. And we have the horizontal speed, which is 23. So now we can calculate the time. So it's 184 divided by 23. So it takes 8 seconds for the ball to travel from position A to position B. So now we can find the height of the cliff using this equation. D is equal to V initial t plus 1/2 AT squared, but in the y direction. Now V initial is basically 0. So the height is 1/2 AT squared. You can just simply use that equation to find the height of the cliff. Now dy is technically negative, and a is negative, but the two negative signs will cancel. So this is just going to be 1/2 times 9.8 multiplied by 8 squared, which is the time. So the height of the cliff is 313.6 meters. So this is the answer. If you plug in negative 9.8, you'll get that dy is negative 313.6. But what that simply means is that the ball travels 313.6 meters in the negative y direction. That's it. So the height of the cliff is this number. So B is the right answer. Number 9. A truck slowly speeds up from 15 kilometers per hour to 95 kilometers per hour in 2 minutes. What is the average acceleration of the truck in meters per second squared? Acceleration is the change in velocity divided by the time it takes to go from V initial to V final, or the change in time. The final speed is 95 kilometers per hour. The initial speed is 15 kilometers per hour, and the time is 2 minutes. So 95 minus 15 is 80. 80 divided by 2 is 40. So the acceleration is 40 kilometers per hour per minute. So now we need to take this value and convert it to meters per second squared. There's 1,000 meters per 1 kilometer. So we can cancel the unit kilometers. So we have meters, which is good, but now we need to convert time into seconds squared. So let's start with minutes. 1 minute is equal to 60 seconds. So this unit is gone. Now the last thing we need to do is convert hours into seconds. So 1 hour is 60 minutes. And finally, 1 minute is 60 seconds. So now we're left over with meters over seconds times seconds. Second times second is basically second squared. So we have meters over second squared. We have the right unit that we want. Now we just got to do the math. So it's going to be 40 times 1,000 and then divided by 60 3 times. Or you could say divided by 60 to the third power. So the acceleration is 0.185 meters per second squared. So this is the answer, which correlates to answer choice A. Number 10. Which of the following expressions can be used to calculate the acceleration of the block on the inclined plane shown below? So what we need to do is draw a free body diagram. So here we have the normal force exerted by the inclined plane on the block. And here this is the force of gravity parallel to the incline. So that's just a component of the weight force. So this is the actual weight force, mg. Let's turn it into a right triangle. So this angle is the same as the angle here. Now this side is adjacent to the angle, so that's going to be the hypotenuse times cosine theta. So that's mg cosine theta. And opposite to the theta, we have this side, which is going to be mg sine theta. Based on SOHCAHTOA, sine is opposite divided by hypotenuse. So what this tells us is that the normal force is equal to mg cosine theta. And Fg is parallel to mg sine theta, so those two are equivalent. Now let's define this as the y direction and this as the x direction. So the net force in the x direction is only equal to this force. There's no other forces in the x direction. And based on Newton's second law, F is equal to ma. The net force is always the mass times the acceleration. And Fg is mg sine theta. So now we can cancel the mass. So the acceleration does not depend on the mass in this problem. Rather, it depends on the angle theta. So the acceleration is g sine theta, which means that answer choice D is the right answer. Number 11. An 8 kilogram box lies on a 30-degree frictionless inclined plane as shown below. What is the final speed of the block as it slides down the inclined plane starting from rest for a distance of 200 meters? So based on the last problem, we know how to calculate the acceleration. It's g sine theta. It's dependent on the angle of the inclined plane. G is 9.8 and the angle is 30. So it's 9.8 times sine 30. Sine of 30 degrees is 1/2. 1/2 of 9.8 is 4.9. So that's the acceleration of the block down the incline. Now it's going to travel a distance of 200 meters down the incline. So our goal is to calculate the final speed. So we could use this equation. V final squared is equal to V initial squared plus 2AD. We have the acceleration, we have the displacement, and the block starts from rest, so we know the initial speed is 0. So this is going to be 0 plus 2 times 4.9 times 200. So that equals the square of the final speed. So 2 times 4.9 times 200, that's 1960. Now the next thing we need to do is take the square root of both sides. So the final speed is 44.27 meters per second. So that's the answer, which matches answer choice D. Number 12. A tension force of 500 newtons acts on a 20 kilogram block, pulling it to the right. A constant kinetic frictional force of 140 newtons acts on the block. What is the acceleration of the block? So let's draw a picture. So let's say this is the block. And we're going to pull it to the right with a rope. So there's a tension force of 500 newtons that acts on the block. And friction opposes motion. So when the block slides on the surface to the right, there's going to be a constant kinetic frictional force, which I'm going to call Fk, and that's going to be 140 newtons. So keep in mind, friction always opposes motion. So if the block is sliding to the right, the kinetic frictional force is directed to the left. If the block is sliding to the left, kinetic friction will point to the right. So how can we calculate the acceleration of the block? First, we need to write an expression for the net force acting in the x direction. Now there's two forces. We have an applied force F, or we call it T because technically it's a tension force. And that force is positive because it's pointing in a positive direction. And then Fk, which is negative because it's pointing in a negative x direction. So the net force in the x direction is going to be the tension force, which is 500 newtons, minus kinetic friction, which is 140 newtons. So therefore the net force is 360 newtons. Now based on Newton's second law, the net force is mass times acceleration. And the mass is 20. So the acceleration is going to be 360 divided by 20. So we can cancel a 0. So it's really 36 divided by 2, which is 18 meters per second squared. So as we could see, answer choice B is the right answer. Number 13. Which of the following statements is true concerning an object moving in a straight line in a positive x direction with constant speed? So if the speed is constant, and if the object is not changing direction, then the acceleration in that direction is 0. And based on Newton's second law, the net force is equal to mass times acceleration. So if the acceleration is 0, then the net force has to be 0. So anytime you have an object moving in a straight line with constant speed, the acceleration is going to be 0. And the net force is 0. So A and C are true statements. B is a false statement, and D is false. An object has mass, and as a result, it has a weight force, which is mg. And that weight force is balanced by the normal force on a horizontal surface. So the normal force is not 0 on a horizontal surface. It's equal to the weight force of the block if there's no other forces acting on it. Now, friction doesn't have to be 0. The block, or the object, could have an applied force of 200 newtons. and the kinetic frictional force could be the same, 200 newtons. And so the net force, which is the difference between these two, it's going to be 0. The net force can be 0, which means the acceleration can still be 0, even with friction present. A good example of this is, imagine if you're driving your car and you're going at 45 miles an hour. And you're not accelerating, you're not speeding up or slowing down, but you're maintaining that speed. Your foot is still on the pedal. You still have to apply gas to the car to keep it moving at 45 meters per second, or 45 miles per hour. The two are not the same, by the way. So let's say if you're going at 45 miles per hour, you still have to put gas to the car. And the reason why you have to do that is because friction is trying to slow down the car. So when you're moving at constant speed, the force that the engine applies to accelerate the car, it's equal to the force, basically to the total frictional force acting on the car, which could be air resistance, drag force, just all of the retarding force that slows down the car. Kinetic friction really doesn't apply to the wheels of the car, by the way. So the things that slow it down will be air resistance and the friction between the gears and everything else. But the net frictional force acting on the car will just balance the applied force by the engines, and so the car will move at constant speed. So the point is this: the acceleration can still be 0 even though there's a frictional force acting on it. So the frictional force doesn't have to be 0. So B and D are false statements. A and C are correct, so therefore the best answer is E. 2 of the statements above are true. So E is the right answer. Number 14. A 25 kilogram block rests on a horizontal surface. A tension force of 135 newtons is applied on a block in the positive y direction to pull it up. What is the normal force acting on a block? So let's draw a picture. So let's say this is the 25 kilogram block, and there's an upward tension force that's acting on the block to lift it up, and that tension force is 135 newtons. How can we calculate the normal force? Well, we need to draw a free body diagram. We need to identify all forces acting on the block. So we have the weight force, which is mg, and also there's the force that the ground exerts on the block, and that's the upward normal force. So the net force in the y direction is the sum of these three forces. We have an upward normal force, so that's going to be positive Fn, an upward tension force, so that's positive as well, and the weight force is in a negative y direction, so it's a negative mg. Now, it's good to determine what the weight force is, because if the tension force exceeds the weight force, the block will no longer be on the surface. It's actually going to lift off from the surface, and there isn't going to be any normal force. However, there will be a normal force if the tension is less than the weight force. So let's calculate the weight force. The weight is mg. It's the mass, which is 25, times the gravitational acceleration of 9.8 meters per second squared. So 25 times 9.8 is 245 newtons. So notice that the tension force is less than the weight force. So there is a normal force in this problem. So let's go ahead and calculate that normal force. Now, because the tension force is less than the weight force, the block remains at rest, which means the net force in the y direction is 0. So 0 is equal to Fn plus T minus mg. Now let's solve for Fn. Let's isolate it. So if I'm going to move T from the right side to the left side, and the same thing with negative mg. So negative mg is on the right side, but on the left it's going to be positive mg. And T is positive on the right side, so it's negative on the left. So the normal force in this example is the difference between the weight force and the tension force. Now we know the weight force is 245 newtons. It's 25 times 9.8 minus the tension force of 135 that will give us the normal force of 110 newtons. So in this case, answer choice A is the right answer. Number 15. A car is currently located 350 meters west of town XYZ. At this instant, it is traveling east at 25 meters per second with a constant acceleration of 3 meters per second squared in a positive x direction. What will be the position of the car relative to town XYZ after 12 seconds? So let's say this block represents the car. And let's say here is town XYZ. So town XYZ on the x-axis will be position 0. The car is currently located at a position of negative 350 meters because it's 350 meters west of town XYZ. Our goal is to calculate the final position of the car after 12 seconds. It could be at position A, it could be at B, it could be at C, or it could be at D. We have to find out where the car will be relative to town XYZ. So what equation can we use in this example? Displacement is equal to the initial speed multiplied by the time plus 1/2 at squared. Now the displacement is also equal to the final position minus the initial position. So we therefore have this equation. So the final position is equal to, I'm going to move this to the right side, so it's going to be equal to the initial position plus the initial velocity multiplied by the time plus 1/2 at squared. This is the equation that you want to use to calculate the final position of the car relative to town XYZ. So let's go ahead and plug everything in. The initial position is the negative 350. The initial velocity of the car is 25 meters per second. And it's going to be traveling for 12 seconds. And the acceleration in the x direction is positive 3. And t is still 12. So this will give us the final answer. So all you got to do is plug this in your calculator exactly the way you see it. And this will give you positive 166 meters. So the car should be somewhere in this vicinity. It's 166 meters to the right of town XYZ after 12 seconds. So D is the right answer. Number 16. A ball is kicked at 25 meters per second from the ground at a launch angle of 20 degrees. What other launch angle will yield the same range at 25 meters per second? So how can we find the answer? Well, this is one of those problems where you just have to know how to do it. The range will be the same when the two launch angles add up to 90. So to find the answer, it's 90 minus 20. So it's going to be 70. So C is the right answer. So a 10-degree launch angle will have the same range as an 80-degree launch angle because 10 plus 80 adds up to 90. A 30-degree launch angle will have the same range as a 60-degree launch angle. And a 40-degree angle will have the same range as a 50-degree launch angle. And by the way, make sure you know this. The maximum range occurs at a launch angle of 45. So that will give you a max range of any projectile whenever it's launched at that angle. 17. How much work is required to speed up a 10-kilogram block from rest to 16 meters per second? So how can we find the answer for this problem? Well, there's different ways you can do it. One way is to use this equation. Work is equal to the change in the kinetic energy of the object. The change in kinetic energy is the difference between the final kinetic energy of the object and the initial kinetic energy of the object. Now the object, or the block, was initially at rest, so the initial kinetic energy is 0. So the work is simply equal to the final kinetic energy, which is 1/2 mv squared. So it's 1/2 times a mass of 10 multiplied by a final speed of 16 meters per second squared. Half of 10 is 5, and 5 times 16 squared is 1280 joules. So therefore E is the right answer. Number 18. How much work is required to lift a 15 kilogram rock 12 meters above the ground? So let's say this is the rock, and we want to lift it up 12 meters above the ground. How much energy, or how much work is required to lift it up? The work required to lift something up at constant speed is equal to the change in the potential energy of the object. So work is equal to mg times the change in height. So the mass is 15 kilograms, g is 9.8, and the change in height is 12 meters. So it's simply 15 times 9.8 times 12. And so the work required is 1,764 joules. So that's all you got to do for this problem. So B is the right answer. 19. Which of the following statements is associated with Newton's third law of translational motion? Is it A, B, C, D, or E? Well, let's look at answer choice A. An object at rest will remain at rest unless acted on by a net force. Well, that's associated with Newton's first law of motion, not his third law of motion, so A is out. Answer choice B says, the acceleration of an object is directly proportional to the net force acting on it. That's a true statement, and it's associated with his second law, not his third law, so B is out. So this equation is associated with Newton's second law of motion. The net force is mass times acceleration. So if you increase the net force acting on an object and the mass is held constant, the acceleration will increase directly. So acceleration and net force are directly proportional to each other. Now, if you increase the mass of the object while keeping the net force the same, the acceleration will decrease. So mass and acceleration are inversely related. And that's the basic idea behind Newton's second law of motion. Now, what about answer choice C? The net force acting on an object is equal to the rate of change of the momentum of the object. Now, this too is related to Newton's second law of translational motion. So let's start with this equation. Net force is mass times acceleration. Acceleration is equal to the change in velocity divided by the change in time. It's v final minus v initial over t. So therefore, the net force is mass times the change in velocity divided by the change in time. Momentum is mass times velocity. So mass times the change in velocity represents the change in momentum. So the change in momentum divided by time is equal to the net force of the object. So this too is related to Newton's second law of motion. Now what about D? An object at rest, or rather an object in motion, will continue in motion unless acted on by net force. That's associated with Newton's first law of motion. So by elimination, the answer has to be E. For every action force, there is an equal and opposite reaction force, which acts not on the same object, but on different objects. So let's say A is the action force. The reaction force is going to be equal to the action force, but it's going to be opposite in direction. So if one is positive, the other is negative. Number 20. Which of the following equations represents the acceleration of the two blocks in the system shown below? Now, there's no friction in this problem. There's no friction on the horizontal surface, and there's no friction between the rope and the pulley. Now, we're going to ignore the inertia of the pulley. So we're just going to assume the pulley has no mass. It's a massless pulley. How can we calculate the acceleration of the system? I'm going to show you two ways. A quick and simple way in case you have a multiple choice test, but for those of you who have a free response test, I'm going to show you another way in which you can calculate the acceleration by drawing free body diagrams. So here's the easy method. Based on Newton's second law of motion, we know that net force is mass times acceleration. So acceleration is net force divided by mass. Now, there's only one driving force for this whole system, and that is the weight force of block 2. The weight of block 2 causes the entire system to move in this direction. And so that weight force is the mass of block 2 times g. So it's m2g. And then you got to divide it by the total mass of the system. That's m1 plus m2. So that's going to give you the acceleration of the system, which is answer choice B. So B is the right answer. So now let's get the same equation using free body diagrams. So I'm going to erase everything. So if you need to go back to this point in the video, just rewind it. So here's M2 and this is M1. So let's focus on mass 2. We have a downward weight force, which is M2G, and an upward tension force, which we'll call T2. The net force acting on block 2, that's in the y direction, and it's equal to the upward tension force, which is going to be positive T2, since it's going in a positive y direction, and this is going to be negative M2G, because it's going in a negative y direction. Now the net force is mass times acceleration. Now we can call it AY, but the acceleration acting on block 2 is the same as the acceleration acting on block 1. Now this acceleration, though, it has to be negative because it is going in a negative y direction. So the net force in the y direction is negative ma, because that net force has to be negative. So let's isolate T2 in this example. So let's take this term and move it to that side. So T2 is going to be M2G minus, this is supposed to be M2A because we're dealing with block 2. So this equation allows you to calculate the tension force that's in the rope. By the way, this is also T2. The tension force acting on this block is the same as the tension force acting on that block. So I guess you could just call it T because they're the same. But since I've used T2 already, I'm just going to keep it T2. Now let's focus on block 1. The net force acting on block 1 is equal to the tension force because this is the only force that's pulling block 1. And this force is in the x direction. And net force is mass times acceleration. And because that net force is in the positive x direction, this is going to be equal to positive ma, but m1a. So T2 is equal to m1a. Now what I'm going to do is replace T2 with m1a in this equation. So we now have that m2g minus m2a is equal to m1a. Now let's take this term and move it to that side. So m2g is equal to m2a plus m1a. Now our next step is to factor the GCF, the greatest common factor, which is a. So m2g is equal to a times m2 plus m1. Now to get a by itself, we need to divide both sides. by m2 plus m1. So the acceleration of the system is m2g divided by m1 plus m2. So this is the answer. Number 21. A car travels around a curve of radius 500 meters at a speed of 15 meters per second. Calculate the centripetal acceleration of the car. The formula that we need to calculate centripetal acceleration is v squared divided by r. So whenever an object moves around in a circle, even at constant speed, there's still going to be a centripetal acceleration. So let's say it's moving in this direction. So that's the tangential velocity of the object. The centripetal acceleration always points towards the center of the circle. And so the object is going to change direction. So make sure you understand that it always points everywhere towards the center of the circle. So the velocity is 15 and the radius is 500. So it's going to be 15 squared over 500. And so the centripetal acceleration is 0.45 meters per second squared. So B is the right answer. Number 22. A 5 kilogram box slides on a horizontal surface with a coefficient of kinetic friction of 0.15 at an initial speed of 12 meters per second. How far will the box travel before coming to rest? So feel free to pause the video and try this problem. So let's draw a picture. So here's the horizontal surface that has friction. And let's say that the box is moving to the right with a speed of 12 meters per second. Now friction opposes motion. So kinetic friction is going to be directed towards the left. And we have a 5 kilogram box. So how can we calculate how far this object will travel before coming to rest? So how can we calculate D? Well, first we need to calculate the acceleration. So we need to calculate the net force in the x direction. The only force in the x direction is the frictional force, and it's pointed in the negative x direction. So the net force is negative Fk. And based on Newton's second law of motion, net force is mass times acceleration. Now Fk, we can replace that with mu k times the normal force. Now the normal force has to be equal to the weight force because the net force in the y direction is 0. So we can replace Fn with mg. So therefore we could cancel the mass on both sides. And so the acceleration of this box is negative mu k times g. The acceleration is negative because the box is slowing down to rest. It's decelerating. So the acceleration is going to be negative. Mu k is 0.15 multiplied by the gravitational acceleration of 9.8 meters per second squared. And so the acceleration is negative 1.47 meters per second squared. So now we can use kinematics to calculate the displacement. We know the initial speed is 12, and because the box comes to rest, the final speed has to be 0. So we can use this equation. V final squared is equal to V initial squared plus 2AD. The final speed is 0. The initial speed is positive 12. The acceleration is negative 1.47. And now we can calculate D. And let's not forget to square this number. So 12 squared is 144. And 2 times negative 1.47, that's negative 294 times D. So let's move this term to the left side so it becomes positive. So we have positive 2.94D is equal to 144. So 144 divided by 2.94, that will give us the displacement, which is 49 meters. So that's how far the box will travel before coming to rest. So B is the right answer. Number 23. A 2-kilogram ball attached to a 1.5 meter long string moves in a horizontal circle at 15 meters per second. What is the tension in the string? So let's draw a picture. So here's the string, and here's the ball, and it moves in a nearly horizontal circle. Now this is the tension in the string. Now we do have the weight force of the ball, which we need to take into consideration, and the tension has an X component and it has a Y component. And here's the angle theta. If the ball is moving very fast, Ty will be insignificant, so the tension in the string is approximately equal to Tx. Now notice that Tx points towards the center of the circle, so Tx provides the centripetal force. So Ty is equal to mg, and Tx is equal to the centripetal force, which is mv squared divided by r. And once we find Tx and Ty, we can calculate T. So let's start with Ty. The mass of the ball is 2 kilograms, and G is 9.8. So Ty is 19.6 newtons. So that's the first thing we need to do. Now let's calculate Tx. So we have a mass of 2. The speed of the ball is 15 meters per second, and the radius of the circle is the length of the string, which is 1.5. So Tx, I'm running out of space here, is 300 newtons. So now we can find T. Notice that this forms a right triangle. So T is the square root of Tx squared plus Ty squared. So that's going to be the square root of 300 squared plus 19.6 squared. So T is 300.6 newtons. So as we can see, T and Tx, they're very close to each other. But the exact answer is answer choice D. We could round that to 301. It's a little bit higher than Tx, but not by that much. 24. What is the maximum speed at which a car can safely round a curve of radius 400 meters? So let's say this is the curve that the car is traveling. It's making a turn. And to make this turn, it needs to exert a centripetal force, which is directed towards the center of the circle. Now, what provides the centripetal force in this particular example? We see that when a ball travels around a circle through a rope, tension provides the centripetal force. Tension in the rope causes the ball to turn. In this case, the static friction between the tires and the road allows the car to turn. So static friction provides the centripetal force in this example. So what we need to do is set static friction equal to the centripetal force. Static friction is mu s times the normal force. Now granted, static friction is an inequality. It can exist from 0 up to its maximum value, which is mu s times the normal force. And we need to use that maximum value because we're looking for the maximum speed. The centripetal force is mv squared over r. It's mass times the centripetal acceleration. The normal force is mg, since the surface is flat. And we could cancel m. Now we need to isolate v. So let's multiply both sides by r. So these will cancel. And so v squared is equal to mu s times rg. So the maximum speed is going to be the square root of mu s times the radius times g. In this example, mu s is 0.2, the radius is 400, and g is 9.8. So the maximum speed is 28 meters per second. So therefore C is the right answer. 25. Which of the following statements is not true concerning a ball that is thrown straight upward into the air? So let's draw a picture. So the ball goes up and then it goes back down. Let's call this point A, point B, and point C. So let's look at each statement. Answer choice A says the speed of the ball is decreasing as the ball travels upward. Is that true or false? That is a true statement. Now we're looking for the false statement. And B says the speed of the ball is increasing as the ball travels downward. That is true. Whenever an object moves away from the ground, the speed decreases. And whenever it moves towards the ground, the speed will increase. But let's understand why. Whenever the acceleration and the velocity vectors have the same sign, that is, if they're pointed in the same direction, the object will speed up. So if the acceleration and velocity are both positive, or if they're both negative, the speed will increase. Now the object will slow down if the acceleration and velocity vectors have different sides. Either they're both positive and negative or negative and positive. So if the signs are different, it's going to be slowing down. So let's analyze the first part of the trip. So from A to B, when the ball is going up, the acceleration is negative because gravitational acceleration is always downward. AY, the acceleration in the y direction is negative 9.8 meters per second. Gravity brings things down. So the acceleration for the left side and the right side will always be negative. Now what about the velocity? In the first half, the ball is moving upward, so the velocity is positive. And during the second half of the trip, it's moving downward, so the velocity is negative. So during the first half, notice that the acceleration and velocity vectors are different. So in the first half, the object is slowing down, the speed is decreasing. So A is true, the speed of the ball is decreasing as the ball travels upward, because acceleration is negative but velocity is positive. Now for the second half of the trip, the acceleration and velocity have the same signs, and so the speed is going to be increasing. It's going to be moving faster. And so B is true, the speed of the ball is increasing as the ball travels downward. Now what about C? The velocity of the ball is 0 at the maximum height. And that is true. In order for the velocity to change from a positive value to a negative value, it has to cross 0. So let's say if you're at positive 5 and you want to get to negative 3, and you can't skip numbers, you have to go through 0. And that's going to occur at point B. The velocity is going to be 0. Now because the ball is thrown straight up, there's only a vertical speed, meaning everything, when I talk about V, it's really Vy. There's no Vx in this problem. It's not moving in a horizontal direction. It's completely moving in vertical direction. And at the top, the vertical speed is 0. And because there's no x component, we can say therefore the speed is 0. If Vx is 0, then V becomes the square root of Vy squared. So V equals Vy when there's no horizontal component. So C is a true statement. Now what about D and E? D says the velocity of the ball is decreasing as the ball travels upward. And E says the velocity is increasing as the ball travels downward. So which statement is true? Is it D or E? And which one is false? Well, let's redraw this picture. Now, before we do that, what you need to understand is that whenever the acceleration is positive, the velocity, not the speed, but the velocity, is always increasing. Remember, speed is the absolute value of velocity. Velocity can be positive or negative, but speed is always positive. Whenever the acceleration is negative, the velocity is always decreasing. Now, because gravitational acceleration is always negative, the velocity should always be decreasing, and it should never be increasing. So therefore, D is the true statement, but E is the false statement. The velocity can't be increasing for an object that is in projectile motion, where gravity is the only influence on the object. So E is the false statement, which means E is the answer. Now let's explain this using numbers. So here the ball goes up, and then it goes back down. Now, even though it looks like it's moving towards the right, assume that it's going straight up and then straight down. We know the acceleration in the y direction is a negative 9.8. So let's say the upward vertical speed initially is 29.4. 1 second later, the vertical velocity will decrease by 9.8. So 1 second later, it's going to be 19.6. And then another second later, it's going to be 9.8. And at the top, the vertical speed is going to be 0. And then at this point, another second later, it's going to be negative 9.8, the velocity. And here, another second later, the velocity will be negative 19.6. So this is at a time of 0. This is 1 second, 2 seconds from the beginning, 3 seconds, 4 seconds, and then 5 seconds. So 6 seconds later, the velocity will be negative 29.4. So notice that the velocity is always decreasing. In the first half, when the ball is going up, the velocity changes from 29.4 to 0. So it's decreasing during the first half. And during the second half, it's still decreasing from 0 to negative 29.4. So the velocity is always decreasing. Now, speed is the absolute value of velocity. So if we turn these values into values for speed, the left side won't change, but the right side will simply become positive. So now, answer choice A says the speed is decreasing as the ball travels upward. That is true. As we go from 29.4 to 0, the values are decreasing. B says the speed of the ball is increasing as the ball travels downward. As you go from 0 to 29.4, the numbers are increasing. So to understand this question, it's important to keep in mind that speed is always positive, but velocity can be positive or negative. So to review, the change in velocity depends on the sign of acceleration. If acceleration is positive, the velocity is always increasing. If the acceleration is negative, the velocity is always decreasing. Now, to determine if an object is speeding up or slowing down, you need to look at the signs of acceleration and velocity. An object is speeding up if the acceleration and the velocity have the same signs, if they're both positive or both negative. And the object is slowing down if the signs of these two are different, if the acceleration is positive and v is negative, or if it's the other way around, if the acceleration is negative and v is positive. 26. What is the direction of the centripetal force at point D in a circle shown below? So we're assuming the object is moving with circular motion. We don't know if it's moving in the clockwise direction or in a counterclockwise direction. And technically, it's not really important what direction it's moving in. What we need to realize is that the centripetal force always points towards the center of the circle. So at point D, it has to point towards the right, which means it's pointed in an eastward direction. So A is the right answer. So let's say if we're somewhere here, the centripetal force will point in a northeast direction between D and C. At A, it would point south. At B, it would point west. And at C, it would point north. So at, let's say, somewhere between B and C, it would point in the northwest direction. Between A and B, it would point in the southwest direction. Between A and D, in the southeast direction. So based on where you are in a circle, you can always determine the direction of the centripetal force. It always points towards the center of the circle. So A is the right answer in this problem. 27. What is the effect on the kinetic energy of an object if the speed doubles? Well, first you need to know the formula. Kinetic energy is equal to 1/2 the mass of the object times the square of the speed. Now notice that kinetic energy is proportional to the square of the speed. So if you double the speed, plug in 2 for V. 2 squared is 4. The kinetic energy should increase by a factor of 4. So B is the right answer. Now let's say, for instance, if you double the mass. What you could do is everything that doesn't change, replace it with a 1, including the 1/2. So if you double the mass, the kinetic energy will double. Now what if you double the mass and triple the speed? So don't worry about the 1/2. Just replace m with 2 and v with 3. 3 squared is 9. 2 times 9 is 18. So if you double the mass and triple the speed, the kinetic energy will increase by a factor of 18. 28. Two objects with masses m are separated by a distance r, and the gravitational force between them is F. Which expression represents the gravitational force acting on each object if the masses are now 3m and 4m separated by a distance of 1/2 r? So here's the situation before. We have two objects with the same mass, that is mass m, and they're separated by a distance r. That's the distance between the centers of the two masses. And gravity brings things together. So gravity is a force of attraction. Now what happens if the first mass triples in value? So it's going to be 3m, and the second mass is 4 times its value, it's 4m, and the distance is reduced to 1/2 of its original value. So the two masses are brought closer together. What is the new force? Well, first we need an equation. The gravitational force between two objects is G times m1 m2 over r squared. Now G is a constant, so we're not going to worry about it for a problem like this. So the first mass triples. For any constants, just replace it with a 1. The second mass increases by a factor of 4, and the distance is reduced by 1/2. Now 3 times 4 is 12. 1/2 squared is, we know 1 squared is 1, 2 squared is 4, so it's 1/4. If we multiply the top and bottom by 4, 1/4 times 4 is 1, 12 times 4 is 48. So it's 48 times its original value. So the answer is E. It's 48F. Now each force will be the same. So this force acting on the 3m object is 48F. The other one will be 48F as well. 29. An object with mass m and speed v travels around a circle of radius r. The centripetal force acting on this object is 500 newtons. What is the new centripetal force acting on the object if the speed is doubled, the mass is tripled, and the radius of curvature is reduced to 1/2 of its original value? So how can we do this problem? Well, once again, we need the equation for the centripetal force. The centripetal force is the mass times the square of the speed divided by the radius. So the mass is tripled, let's replace it with 3. The speed is doubled, so let's replace v with 2. And the radius is reduced to 1/2 of its original value. 2 squared is 4. and 3 times 4 is 12. 12 divided by a half is the same as 12 times 2. If we multiply the top and bottom by 2, 1 half times 2 is 1, 12 times 2 is 24. So the centripetal force is 24 times its original value. Now the original value, we have it, it's 500. So the new value is going to be 500 times 24. Which is 12,000 newtons. So that's the new centripetal force. D is the right answer. Number 30. A satellite orbits the Earth at 4,500 kilometers above the surface of the planet. The mass of the Earth is 5.98 times 10 to the 24 kilograms, and the radius of the Earth is 6.38 times 10 to the 6 meters. What is the speed of the satellite? So let's draw a picture. So let's say this is the Earth, and this is the satellite orbiting the Earth. So this is the height of the satellite. Now, what provides the centripetal force in this problem? What keeps the satellite in circular motion around the Earth? The answer is gravity. Gravity provides the centripetal force. Earth exerts a gravitational force on the satellite that keeps it moving in a circle. The satellite wants to fly off towards outer space, but the gravitational force pulls it in that direction. Whenever the velocity and force vectors are perpendicular, the object turns, and so we have circular motion. So knowing that, we could set, I'm going to need more space, so let me just erase this for now. We could set the gravitational force equal to the centripetal force. Now the gravitational force between two objects is the gravitational constant times the mass of the object, let's say the mass of the Earth, and the mass of the satellite, divided by the square of the distance between their centers. The centripetal force is acting on the satellite, not the Earth, because the satellite, it orbits the Earth. So the centripetal force is mv squared over r, where m is the mass of the satellite, v is the speed of the satellite, and r is the same as this r, the distance between the two centers of the two objects. That's what I meant to say. So let's cancel the mass of the satellite, and we can cancel 1r value on each side. So we're going to have this left over, g times the mass of the Earth divided by the radius of the circle, and that's equal to v squared. So now let's take the square root of both sides. So the speed of the satellite is the square root of g times the mass of the Earth divided by r. Now what is r in this problem? R is not the radius of the Earth. It is the radius of the satellite's orbit, with Earth being the center. So this is the radius of the Earth. Let's call it lowercase r. And this is the height of the satellite above the Earth's surface. So this r is the sum of little r and h. So it's the distance between the center of the Earth and the center of the satellite. So the radius of the satellite's orbit is going to be the radius of the Earth plus the height of the satellite above the Earth's surface. Now, the radius of the Earth is in meters, and the height of the satellite is in kilometers, which we need to convert to meters. 1 kilometer is 1,000 meters, so we're going to multiply this by 1,000. 4,500 times 1,000 is 4.5 million, or 4.5 times 10 to the 6. 10 to the 6 is 1 million. So if we add these two numbers together, this is 1.088 times 10 to the 7. Or you could say 10.88 times 10 to the 6. It's the same. So now we can calculate the speed of the satellite. So g, the universal gravitation constant, is 6.67 times 10 to the minus 11. The mass of the planet is 5.98 times 10 to the 24 kilograms. And r is 1.088 times 10 to the 7. So go ahead and plug in these numbers. So the speed of the satellite is 6,054.8 meters per second. So this corresponds to answer choice D. 31. A horizontal spring is compressed 45 centimeters by a 12 kilogram block. How fast will the block travel as soon as it is released by the spring? Well, let's draw a picture. So let's say this is the spring. And let's say there's a block attached to it. So right now the spring is compressed. And this is a 12 kilogram block. Whenever you compress a spring, you're storing potential energy. And once the spring is released, that potential energy is converted to kinetic energy. Our goal in this problem is to find the final speed of the block as soon as it's released from the spring. So we need to set elastic potential energy equal to kinetic energy. The elastic potential energy of the spring is 1/2 kx squared, where k is the spring constant, x is the amount that it's stretched or compressed relative to its natural length. The kinetic energy of the block is 1/2 mv squared. So we can cancel the fraction if we multiply both sides by 2. Now we have the spring constant k, it's 500 newtons per meter, and x, the amount that it's compressed, which is 45 centimeters, we need to convert that to meters. We need to make sure that these units match. So to convert centimeters to meters, simply divide by 100. 45 divided by 100 is 0.45. And don't forget to square it. The mass of the block is 12. So now we could calculate V. So first, let's multiply 500 by 0.45 squared. So that's going to be 101.25. And that's equal to 12 times V squared. So we need to divide both sides by 12. 101.25 divided by 12 is 8.4375. So now we need to take the square root of both sides. So this will give us the final speed, which is about 2.9 meters per second. So that's the answer to this problem. Answer choice C. 32. A ball is kicked with a speed of 40 meters per second at an angle of 30 degrees from a 500 meter cliff. How fast is the ball moving just before it hits the ground? So let's draw a picture. So let's say that's the cliff, and the ball is kicked up, it goes up, and then it falls back down. So it's kicked at an angle of 30 degrees. And the initial speed of the ball is 40 meters per second. So how can we calculate the final speed just before it hits the ground? Now keep in mind the height of the cliff is 500 meters. Now you can use kinematics because this is a projectile motion type problem, or you can use conservation of energy, which I believe is a lot easier for this problem. So let's call this point A and point B. At point A, the object has potential energy and it has kinetic energy. It has potential energy because it's above ground level, so it has the ability to fall. It has kinetic energy at the beginning because it's moving. So what's really going on in this problem? What's happening is that the potential energy of the object at point A is going to convert to kinetic energy. Now, even though the object already has some kinetic energy, the kinetic energy will be increased. So the final speed of the object at point B is going to be greater than the initial speed. So the answer should be greater than 40, which, if you look at the answer choices, all of them are larger than 40. In this problem, mechanical energy is conserved. So the initial mechanical energy has to equal the final mechanical energy. Mechanical energy is always conserved whenever you have conservative forces acting on the system. The only time mechanical energy is not conserved if there's a non-conservative force like friction or an applied force or tension force. But gravity is a conservative force, so mechanical energy will be conserved. Mechanical energy is the sum of the kinetic and potential energies. So at point A, we have potential energy and kinetic energy. Now at point B, we only have kinetic energy. The final potential energy at point B is 0 because at that point it reached ground level. So this is the equation that we need to calculate the final speed. So the initial potential energy is going to be mgh. The initial kinetic energy is 1/2 mv initial squared. And the final kinetic energy is 1/2 mv final squared. So in this example, we don't need m. We could cancel the mass from every term. Now let's plug in everything that we have. So g is 9.8. The height of the cliff is 500. And then it's going to be plus 1/2 times the square of the initial speed, which is 40 squared. And that's equal to 1/2 times v final squared. 9.8 times 500, that's 4,900. 40 squared is 1,600, and half of that is 800. So that's equal to 1/2 times v final squared. Now 4,900 plus 800 is 5,700. Now to get rid of the fraction, we need to multiply both sides by 2. So 5,700 times 2 is 11,400. The last thing we need to do is take the square root of both sides, and this will give us the final speed. So the final speed of the object just before it hits the ground is 106.8 meters per second. So this correlates to answer choice B. 33. What is the power exerted by the engine of a 1,500 kilogram car moving at a constant speed of 25 meters per second with a constant retardant force of 1,200 newtons working against it? So we have a picture of this vehicle. The engine is going to drive the car forward. And so capital F will represent the force that the engine applies to the car. Lowercase f, I'm going to use it to represent the retardant force, which slows down the car. So the net force in the x direction is the difference between these two forces. The first force is in the positive x direction. That is the applied force, so that's going to be positive. The retardant force is in the negative x direction, so it's going to be negative. Now, whenever an object is moving with constant speed in a straight line, if it's not turning, the acceleration on that object is 0. And we know that the net force is mass times acceleration. So the net force has to be 0. So therefore, if we take this term and move it to the other side, the retardant force is equal to the applied force. So now that we have the applied force of the engine, we can now calculate the power exerted by the engine. Power is the rate at which energy is transferred. So power is work divided by time. And work is force times displacement. And displacement divided by time is velocity. So power is force times velocity. So the power exerted by this engine is going to be the applied force of 1,200 multiplied by the speed of 25 meters per second. And so this comes out to 30,000 watts. So watt is the unit of power. 1 watt is 1 joule per second. Therefore, E is the right answer. 34. A certain laptop uses 150 watts of power. If the cost of electricity is 6 cents per kilowatt hour in town XYZ, what is the cost of running the laptop 4 hours per day for an entire month? Well, let's say a month is about 30 days. So how can we calculate the cost of electricity? We know that power is work divided by time, and so work is power multiplied by time. Now work and energy has the same units. So energy is power multiplied by time. Kilowatt hours is really a unit of energy. Power is in kilowatts. 1 kilowatt is 1,000 watts. And the unit hour is basically a unit of time. So kilowatt hours is a unit of energy. And once you have that, you could find the cost of electricity using this unit of energy. So I'm going to get the answer using the conversion process. Feel free to pause the video if you want to try it. So let's start with the power of 150 watts. Now let's convert it to kilowatts. 1 kilowatt is equal to 1,000 watts. So you want to set it up in such a way that the unit watts cancels. So now we could convert kilowatts into unit of dollars. The cost is 6 cents per kilowatt hour, which is kilowatts times the number of hours. So we could cancel the unit kilowatt. Now we just got to get rid of the time hours. So the laptop is being used 4 hours per day. So right now, this will give us the cost of electricity per day. Now let's convert days to months. In this example, there's 30 days per month. And I'm running out of space. So now we have the cost of the laptop per month. So it's going to be 150 divided by 1,000 multiplied by 0.06 times 4 times 30. So the total cost to run it for 1 month, 4 hours per day every day, is $1.08. So this is the answer. 35. The graph below shows the velocity of the object with respect to time. What is the acceleration of the object at t equals 2 seconds? So we need to find the acceleration at this point. What you need to know is that whenever you're given a velocity time graph, the slope of this graph is equal to the instantaneous acceleration of the object at that point. Now the slope of a line, if you have a straight line, the slope is constant. So the average acceleration is the same as the instantaneous acceleration. Now to calculate the slope, in algebra is represented by the symbol m, is the change in the y values divided by the change in the x values. In this particular example, the y values are basically velocity values. So y2 minus y1 is basically the final velocity minus the initial velocity. And the x values represent time values. So x2 minus x1 is really t2 minus t1, which we can replace it with the change in time. Now the change in velocity divided by the change in time is acceleration. So all we need to do is find the slope of this line, and that will give us the acceleration. Now the time changes from 0 to 3 seconds, and the final velocity is 80, and here the initial velocity is 20. So final minus initial, that's going to be 80 minus 20, and the change in time going from 0 to 3 is 3 seconds. Now 80 minus 20, that's a change in velocity of 60, divided by 3, That's 20. 60 divided by 3 is 20. So the acceleration is 20 meters per second squared. And the acceleration is positive because the velocity is increasing. Whenever the velocity is increasing, a is going to be positive. Here, the velocity is constant, so the acceleration is 0. The slope of a horizontal line will always be 0. And during the third part of the graph, the velocity is decreasing, so the acceleration is going to be negative at that point. Now, if you want to calculate the acceleration for the second part, you can use the velocities at these two parts. So using slope, which is rise over run, the rise is going from 80 to 0. So the rise is negative 80. The run is 4 units. So rise over run, negative 80 over 4. The slope is negative 20. So the acceleration, anytime between 6 and 10 seconds, is negative 20. The acceleration for the first 3 seconds, whether it's at 1 second, 2 seconds, 2.5, it's going to be positive 20. So for this particular problem, the answer is C. That's the acceleration when t is 2 seconds. 36. A force of 30 newtons was applied to a 15 kilogram block initially at rest for 8 seconds. What is the final speed of the block? So let's draw a picture. And here's the block. It's a 15 kilogram mass. And we're going to apply a force of 30 newtons to it. And this force will be applied for 8 seconds. So how can we calculate the final speed? Now we know that the initial speed is 0. So what can we do? Now we can use the impulse momentum formula. Impulse is the force multiplied by the change in time, and momentum is mass times velocity. But the impulse is equal to the change in momentum, so the change in momentum is mass times the change in velocity. So the impulse is going to be 30 newtons multiplied by a time of 8 seconds. The change in velocity is the final velocity minus the initial velocity. 30 times 8 is 240. So the impulse is 240 newtons times seconds. The mass is 15 kilograms, and the initial speed is 0. So 240 is equal to 15 times v final. So we need to divide both sides by 15. 240 divided by 15 will give us the final speed, which is 16 meters per second. And so that's the answer, which correlates to answer choice C. Now you don't have to use the impulse momentum theorem if you don't want to. So I'll show you the other way of doing this. The first thing you could do is calculate the acceleration. Acceleration is the change in velocity divided by the change in time. But let's not use that formula. Let's use this. The net force is equal to mass times acceleration. Now this is the only force in the horizontal direction, so that force is the net force. And we have a mass of 15. So the acceleration is 30 divided by 15, which means it's 2. Now once you have the acceleration, you can now use this formula to calculate the final speed. The initial speed is 0, the acceleration is 2, and the acceleration is acting on this object for 8 seconds. So 2 times 8 will give us a final speed of 16 meters per second. So C is the right answer. 37. A 10 kilogram block moving east at 15 meters per second strikes a 20 kilogram block initially at rest. What is the final speed of the two blocks if they stick together? So let's call this block 1 and block 2. So after they collide, the two blocks will be sticking together. So this is the 10 kilogram block, and this is the 20. So what can we do to find the final speed of the two blocks when they stick together? So this is going to be m1, m2. Actually, let me put this here. Now m2 is initially at rest, so it's not moving. m1 is moving with an initial speed of 15 meters per second. And our goal is to find the final speed. If they stick together, the speed will be the same. Now, during any collision, momentum is conserved. So the initial momentum is equal to the final momentum. Momentum is mass times velocity. So the momentum for object 1 is going to be m1v1. For object 2, it's m2v2. And then you can treat this as one object. So that's going to be the combined mass times the final speed. Now the combined mass is m1 plus m2. So this is the equation that you need anytime you want to calculate the final speed of two objects that stick together after a collision. So now let's plug in the information. The mass of the first object is 10. It has a velocity of 15. If it was moving west, the velocity will be negative. But because it's moving east in a positive x direction, the velocity is positive. The momentum of the second object is 0 because it's at rest. The velocity is 0. And then m1 plus m2, that's going to be 10 plus 20 times v final. Now 10 times 15 is 150. And 10 plus 20 is 30. So to calculate the final speed, we need to divide 150 by 30. So we could cancel a 0, and so this becomes 15 divided by 3, which is 5. So the final speed of the two blocks sticking together is 5 meters per second. So D is the answer. 38. A force of 50 newtons is applied to a 10 kilogram solid disc with a radius of 65 centimeters. What is the acceleration, the angular acceleration of the disc? So let's say if we have a circular solid disc and we're going to apply a force of 50 newtons. This could be a tension force to pull the disc, or you can just apply force in this direction and cause it to turn in that direction. So the direction is really not important in this problem. Now the radius of the disc is 65 centimeters, but we need that in meters. So if we divide that by 100, then that gives us a radius of 0.65 meters. So what formula should we use in order to calculate the angular acceleration of the disc? It's important to know that torque, the net torque, is equal to inertia times alpha, in the same way that the net force is mass times acceleration. Torque is the rotational equivalent of force. Inertia is basically the rotational equivalent of mass. They both provide resistance to motion. Angular acceleration is the rotational equivalent of linear acceleration. So this is Newton's second law for translational motion, and this is Newton's second law for rotational motion. Now there's only one torque acting on this object, and it's created by the force. Whenever a force causes an object to rotate, it creates a torque. And this torque is applied in the clockwise direction, so that's a negative torque. But again, we don't have to worry about the signs in this problem because the angular acceleration is positive. So let's calculate the torque. There's only one torque acting on this object, so it's the same as a net torque. Torque is the force times the lever arm. In this case, the lever arm is the radius. The lever arm is the distance between where you apply the force, or the line of action of the force, which is basically any line in this direction. The line of action is always parallel to the force. So it's the distance between that line of action and the axis of rotation, which is the center of the circle. And that represents the radius of the circle. So the lever arm is the radius in this problem. So the torque is going to be a force of 50 newtons times a lever arm or moment arm of 0.65 meters. So the torque is 32.5 newtons times meters. Now the next thing we need to do in order to calculate the angular acceleration is we need to calculate the inertia of the solid disk. The inertia of a solid disk is 1/2 mr squared. Now the formula changes based on the shape you're dealing with. For instance, the inertia of a sphere is 2/5 mr squared. The mass of the disk is 10 kilograms and it has a radius of 0.65 meters. So the inertia is 2.1125 kilograms times square meters. Now that we have the inertia and the torque, we can calculate the angular acceleration. So alpha, or the angular acceleration, is basically the ratio between the torque and the inertia. So it's going to be 32.5 divided by 2.1125. So the angular acceleration is 15.38 radians per second squared. And so that's the answer for this problem, which correlates to answer choice A. 39. A merry-go-round moving with an angular speed of 1.8 radians per second has a rotational inertia of 100 kilograms times square meters. A child jumps on it, and the rotational inertia of the child and the merry-go-round is now 110 kilograms times square meters. What is the new angular speed of the child on a merry-go-round? So let's say this is the merry-go-round, and here is the axis of rotation. And right now it's spinning at a rate of 1.8 radians per second. So what's going to happen to the angular speed if a child jumps on it? Will the merry-go-round spin faster or slower? That's what we need to figure out. Whenever you add something that's already spinning, if it drops straight down on that spinning device, the angular speed will decrease. And this is due to the conservation of angular momentum. The initial angular momentum has to equal the final angular momentum. And angular momentum is inertia times angular velocity, the same way as linear momentum is mass times linear velocity. So this is the equation that we have. Now notice that the inertia of the merry-go-round increases when the child jumps on it because it's more mass. If the inertia goes up, the angular speed has to go down. So the inertia of the merry-go-round before the child jumps on it is 100, and the angular speed is 1.8 radians per second. The final inertia is 110. So when the child jumps on it, it increases by 10. So from 100 to 110. So now we need to calculate the final angular speed. So it's 100 times 1.8 divided by 110. And so the final angular speed is 1.64 radians per second. So this rounds to 1.6, which means C is the right answer. Number 40. In the figure below, M2 is greater than M1. And let's say the pulley is a massless pulley, and there's no friction. Which of the following equations can be used to calculate the acceleration of the block? So because M2 is larger than M1, the whole system is going to turn in this direction. To find the acceleration, it's going to be the net force divided by the total mass of the system. So there's really two driving forces in the system. The first one is the weight force of the second block, which is M2G, and the second one is M1G. Now we know that the whole system is moving in this direction. So the driving force is M2G. So the weight of block 2 causes the whole thing to move. The weight of block 1 slows it down in that direction. So the net force is the difference between the weight force of those two blocks. And then we need to divide it by the total mass of the system. So that's m1 plus m2. So if we factor out g, it's going to be m2 minus m1 times g divided by m1 plus m2. So C is the right answer. Now I'm going to show you the other way of getting the same answer using free body diagrams, just in case you get this question as a free response question on a test. Now this block is slowed down by an upward tension force, and this one is accelerated by an upward tension force. These two tension forces in this problem is the same if the pulley doesn't have any mass. So if we're not concerned with the inertia of the pulley, then these two tension forces will be equal. So the net force in the y direction for block 2, so I'm going to call it F2, it's equal to the upward tension force minus the downward weight force. And the net force is mass times acceleration, but we're dealing with block 2. Now, because block 2 is moving down, the net force has to be negative m2a, because the net force is directed in the negative y direction. So let's isolate t in this problem. Let's take this term and move it to that side. So t is m2g minus m2a. Now let's do the same for the other block. The net force acting on block 1 is going to be the upward tension force minus the downward weight force m1g. Now block 1 is actually moving in the positive y direction. So the net force is going to be positive m1a as opposed to negative m1a. So therefore, if we take this term and move it to that side, the tension force is the sum of the net force plus the weight force acting on block 1. So here's the second equation that we need. Since these two expressions equal t, we could set them equal to each other. So m2g minus m2a is equal to m1a plus m1g. Now every term that has an acceleration, let's move it to the right. Every other term, let's move it to the left. So I'm going to take this term, move it to the right. And so on the right side, it's going to be positive m2a. So I have m1a plus m2a. And this term doesn't have an acceleration, so I'm going to move it to this side, where it's going to become negative. So on the left, I have m2g minus m1g. So at this point, I need to factor out a. So this is going to be m2g minus m1g, and that's equal to m1 plus m2 times a. Now the last thing that I need to do is divide both sides by m1 plus m2. So now I have this formula. Now I'm going to factor out g, just like I did before. So m2 minus m1 times g divided by m1 plus m2. That's equal to the acceleration of the system. So now you know how to calculate the acceleration of the two blocks for this particular problem.